Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about wind tunnels part 1. If you are interested, I will also make part 2. So what exactly is the need? You have to understand the need before you jump into it. So need is basically rocket has to go through atmosphere. Even though you may think like, oh, rockets is just like it's working in vacuum. Well, no, it has to go through the basically atmosphere. And if you do not understand the atmosphere, max Q is gonna break you. So fundamentally, you have to understand it. And there are many things, and increasingly larger percentage of things that are coming back, be it space shuttle or be it Falcon 9 first stage. So amount of things that are coming back, and we want to live in a world where more and more things are coming back. So fundamentally we have to understand atmosphere even more. It's not just like stay hard and strong enough so you can push through max Q and then it's like bye bye. No, you have to survive re-entry also. So fundamentally the re-entry characteristics and atmospheric flight behavior, yes, these things fly. That's why the angles and geometry and guide fins and all that jazz, grid fins basically, all those are fine-tuned specifically with the aerodynamic characteristics of the body itself. So you need to know these data. And if you do not have that, if you do not have wind tunnel that are suitable for that, at that point in time you are just running on hopes and computer simulation. Now you may like, isn't computer simulation good? Well, one thing you have to understand, computer simulation that normal people deal with is just computer simulation. But what you have to do when you are dealing with like multi-billion-dollar kind of assets, you have to have a feedback loop in that computation model, meaning you have to calibrate that data either with previous model that you have already built. Is in case of jumbo jets, it's like, okay, this is previous data. Is this computer model simulate what we actually get in real life? If the answer is close enough within the margin of error, then you're like, you know what, then this is good, then you simulate something new. But you always need a feedback loop. Without that feedback loop, computer is just guessing, and computer, while they are getting good, they're not infinitely good. So fundamentally they still need feedback loop. And wind tunnel is a very good way of cheap and okay solution for that, meaning you create a wind tunnel, you get data, you feed that data into computer model, and then you can stretch it. Meaning, let's say if your tunnel can only go to Mach 5, you start to get a flow of characteristics of it. You start to get a feel for things. Feed that data into your computer, and computer can simulate what will happen at Mach 6 or Mach 7. And you may find that data would to be far more reliable, because if everything else is projected accurately enough, a computer will know what to do. Computer will know this is how real world reacts. So it would be far more reliable if you have not done that feedback loop. That is why wind tunnels are still used. That's why you will never have a world where people are like, without, we can develop something without wind tunnel. No, you have to have it. So what are the vectors that somebody has to deal with? Well, you have to prioritize what you need, because you cannot have it all. You cannot have a wind tunnel that is huge and has a speed range of going from subsonic to hypersonic. You're not gonna have it. So you have to prioritize what you need. Like first category is speed. For example, if you are developing a car company or truck company, you don't actually need high speed. You're gonna be classified as subsonic or low speed. Basically slow speed as they call it, that is below Mach 1. Basically under no circumstances air can reach Mach 1. Then you are talking about the plane range, which is subsonic. Even though it's subsonic, it means Mach 1.5, because majority of the plane is almost touching that boundary. So you do need that. And if during dive and all that jazz, they do cross sonic barriers, so they need to know that sort of thing. Even though plane supposed to be behind it, it's like almost touching it. So you do want your tool to be like, okay, I can simulate what is going to happen. So subsonic comes from generally under Mach 1.5. Then we come to supersonic. This generally means under Mach 1, basically 5. Then we hypersonic, generally under Mach 15 or even 20. At this point in time, generally most things are pulse based, so you can go very high Mach speed. Now, bigger scale is always better. You want your model to be huge, so you can put sensors inside it. There is no point of making a model data and you're like, all I'm getting is video out of it. People do need data. It's like what kind of temperature we are getting, what kind of basically reaction is happening, what kind of pressure drops is happening. For that you need sensors. Sensors take up space, so you do not want your model to be very tiny. You want them to at least be big enough where you can put some actual data. Otherwise you will go back to the era of Wright brothers wind tunnel. Again, much better than nothing, but you get the point. Like, we do need a bit more data nowadays. So to get a bit more data, you need bigger model. But both of those things cost. You have to figure out what do you need. Then we come to duration of the tunnel. Now, duration of the tunnels are simply means you have a continuous tunnel or pulse tunnel. Pulse tunnels are generally, when you see giant balls, those are generally pulse tunnels. So they can only operate for basically few seconds or few milliseconds. Yeah, if they are really, really fast, only few milliseconds gonna happen. Now, all those data comes to the final conclusion of what we call availability, meaning what is the on time. You could have a tunnel that is like, okay, it's a tunnel, is built for a company, it's specifically built for one thing. You can just keep coming in and keep testing it. Or you could have something that is very specific, testing a re-entry, and you were like, yeah, test this, get as much data as you can, because the next time you're gonna get to try, you may have to wait like 4 days or a week before everything resets. So on time also matters, and be mindful there is only 24 hours in a day. So on time may be important for you or may not be. So you have to vector that also into a calculation. For car company, they may be like, dude, we are doing so many little changes that exponential cost that we have to bear in order to make a continuous tunnel may become justifiable if they are having multiple iterations. So on time is very important for them. For airline companies, like even a tiny model takes, let's say, 1 month to make. They're like, you know what, as long as tunnel can be ready before the model is complete, they're like, dude, we good. So on time also matters. So what about the test area where the main thing happens? So air has weird properties, meaning air starts to behave like a puppy at high speeds. So it creates what we call boundary layer, meaning if my hand is moving like this, air is interacting. If I'm moving my hand very high speed, there is a layer of air curtain, so to say, which we call boundary layer. Now this layer is a very sticky layer. It behaves weirdly. Now that sticky layer sticks to surface. Now you do want to test what will happen if boundary layer sticks to your airframe. Awesome, but here's the it's not gonna only stick to your airframe or test article, it's also gonna stick to the walls of the structure. So that inherently limits it, because you do not want the boundary layer of this puppy making love to this puppy. Because again, if two boundary layers are interacting, that never happens in real life. So your test data will be invalidated, meaning you're gonna get bogus result. So you have to take that into equation. Then shock wave. Shock wave also behaves very different. Like if you have a let's say SLS model and you are testing everything, but let's say tunnel is small. Again, low cost, continuous running, awesome. But again, shock wave starts to bounce back from the walls. This data would be invalidated. So you have to figure all those things out. That's why test area is not as simple as like there is a box, put whatever you need to. You have to figure out there should not be any shockwave rebouncing scenario. There should not be any scenario where you have boundary layers touching other boundary layers. And then we come to the worst aspect, that is choked airflow, meaning you will like, dude, this tunnel is huge. They should be able to put bigger model. Maybe they're not, especially at high speeds. The reason for that is like if they put blockages and like again, air is flowing, you are putting things in there, that's acting as a blockage. Inherently like immovable object with unstoppable force kind of thing is happening. So if you make it large enough, you'll reach what we call choke airflow, meaning you're creating enough constriction there that air changes its behavior, meaning your velocity, pressure and temperature, all three things will change. That will throw off your result, because that does not happen in real world. So that creates a scenario where ideally most optimistic scenario is generally fill up to only 10%. So you have a 100 cubic foot area, only fill up 10% of it, do not fill up 100%. So those things do play a critical role. You have to understand. You can't just like, I'm going to make a big tunnel and put a big asset in that. No, we make big tunnels so we can use at least moderately sized props. That's why like these things are like moderately sized. Like you can handle that in hand. It's not like huge model. They can make it. It's just that at high speed, boundary layers will start to make love to each other. So data will be useless. So at high speed, generally like make small models. So what about the setup? Now setup also is kind of simple but complex at the same time. Simple is like all you need is clean, stable airflow. That's it. You want to clean your air, so you don't have dust particle throwing off the result, and you want a stable airflow. Now, high speed air is kind of easy. You put a jet engine, that's it, done, go home. It's very easy. But it's not stable. It's creating a very noisy air. Noisy as in like it has too much vortexes. That's not good enough. So we need clean, stable airflow. How do we start that? We start with adding power. So you make a tunnel, then you start with an electric motor generally, and you add energy to it. Now you can use one giant motor in some scenarios with giant fan, or sometimes you will have multiple small ones. Both has their own pros and cons. Depending on your engineer's design specification, you want to choose one or the other. Then you have the flow. You got the flow, awesome. Now you have to go send it through what we call turbulence must be removed. Because you have to understand, any propeller, no matter how good or efficient or ugly it is generally going to give you velocity which you want, but it's also going to add turbulence which you do not want. So turbulence must be reduced. So how do we reduce it? We have send it through what we call flow straightener. Basically these are either hexagonal on large scale or like cylindrical structures that are like small pipes, lot of it. Like there is just a wall which has like known size of holes that creates a laminar flow. Now after that laminar flow, there will be a basically mesh network, a wire screen as we call it, basically like jali. Now this wire network is just there to create what we call pressure drop. Now the benefit of pressure drop is the pressure drop happens in like a stabilization way, meaning if there was a current of air that is moving faster, pressure drop will reduce its speed. But if some current was lagging behind, it will also gain that speed. So it's basically stabilizing everything to act as a uniform system. So once you have laminar flow, once you have screened everything for pressure drop, now you have a good thick air. At this point in time, you put geometry. You get what you need to do. Now you put geometry, basically how much compression you want to do, like this choke area, how much you want to do. Depending on your test requirement, you could have, like some test articles have different scale capacity, so they can test different velocity also. So you put that throttle, you have your test article, and it circulates everything. So turbulence must be removed, and you have two options. Either you have open circuit system or closed loop system. Now this is a closed loop system. Most of the wind tunnels are closed loop. Now why the heck we have open loop? It's cheap. If your country does not have enough money to invest in this sort of thing, then it might be cheaper to just build an open loop system, because it's far more cost effective. You can get going now rather than like, okay, 2 years from now we're gonna start. If time is valuable, or just like you do not have the enough capital to invest in it, open becomes viable. Closed loop does save you energy, because again, once the air goes through, so let's say your propeller was adding 50 meters per second of velocity, 50 meters per minute, pardon me, 50 minutes per minute. Now that's a good flow. Now due to all the restriction, flow constraint and all that jazz, you're gonna drop it to, let's say, 30. So but again, here the propeller only has to add 20 more rather than like from 0 to that. So that's why it's far more efficient. Now these things are generally good for only supersonic speed. Even supersonic is kind of pushing it. But if you want to go from high supersonic to hypersonic, in those sort of time, you need what we call tank-based system. Basically this sort of design, which we call blow-off system. So you're going to have a tank which has very dry, basically high pressure air. Then it's going to go to a nozzle that literally looks like a rocket engine nozzle. And then it's going to have a throat, which is going to create a choke flow. And then it's going to have an expansion area. Now, there is an issue with that if you expand high pressure gas that quickly, you may cool it down too much. It's almost like how rocket engine exhaust is very hot when it's going through the throat. The moment it expands, it cools down. Like it can cool down, like if you have high pressure gas, which is not like a reacting gas, you could cool it down so much that air liquefies here. So you may have a heater added here just to make sure that basically air does not turn to liquid nitrogen. So they may need to heat it up to, like, let's say 900 degrees Celsius. Again, be mindful. That's how we liquefy air. We compress this puppy and let it expand. That's what you're doing here. So you do need to add heat. So at that point in time, you get your hypersonic flow. Everything is awesome. Then you'll send it to another choke area. The reason for that is, so this test section, so to say, has a stable system where it's like no changes happening, no boundary shocks are traveling anywhere back or forth. You just want to stabilize it. And then it goes to low pressure zone, and that's why you see balls. So whenever you see giant balls, they are generally made for vacuum holding, meaning you have high pressure tanks and then you have zero pressure vacuum balls. Those suck in the air. So that's why it can work for a few seconds at least. Again, you cannot vent this oomph in atmospheric pressure, because be mindful, atmospheric pressure is 15 psi. That's going to backflow. You can see that in real world rocket. Whenever rocket nozzle comes out, what does it do? Shock diamonds. It bounces backwards. Shock diamond. So you don't want that shock diamond happening here. That's why it needs that vacuum balls. Now, inherently, you can see like that is not a continuous system. Inherently, there would be a limitation. And yes, there is. These are very cost-effective system, but they do not work for minutes. They work for few seconds, and maybe even millisecond if you are really, really high speed. So that's the limitation. The best you have seen is just put a jet engine kind of system. At that point in time, you can go to upwards of Mach 5. But you cannot have like Mach 17, Mach 20 or something like that continuously. Like it can be done if you're really pushing it, but your electrical cost and or maybe test area would become tiny. So there is always a pros and cons. You have to figure these things out. So what are the cost here? Now cost matters here because again, there is no free lunches, it's expensive, is that wind tunnel do have one good advantage, that they have vast user base. What does that mean? That simply means if a nation, let's say USA, invest a lot in making wind tunnels as early as like 1940s, that tunnels will be leased out to other private players, and it's gonna allow them to recoup cost. That's why countries only generally build high quality wind tunnels when it's government assisted. So government investing in that. Think of it this way, like India needs a hypersonic wind tunnel. Who's going to use it? ISRO is going to use it and DRDO is going to use it. Now, neither of them have enough budget to build on their own. However, if Indian government builds it, they're like, okay, now you have two users. But again, neither of them will pay for it. But okay, you have a use case scenario. Now you're going to rent this area to other parts of your either governmental sector or private sector. At that point in time, now you have a money revenue from that. So that's why like many government-based wind tunnels are open for users, for public. Not for public, for you and me, as in like you have to pay for it and you are still talking millions of dollars, but it's chump change compared to if you had to build it your own. So that's why generally government invests so much money into building this sort of thing. They know for a fact that, hey, you build this system, it has many users. They're like, shut up and take my money. It's actually a long-term investment from a country's point of view. This is the Indian government launching it. And to give you a context, what kind of money we are talking about, F1 banned basically full scale and full speed wind tunnels, full speed as in like traveling at 300 kmph, is that there were many big companies like Mercedes and Ferrari, they had wind tunnels that can simulate everything in full scale, meaning they will just put the actual car there. So that is very unfair advantage because they can fine tune things far more effective. They're like, dude, we tested this does not work, we change it. Rather than extrapolate data, they're like, dude, this is real world. This is real world. A treadmill that is working at that speed, airflow that is working at that speed, that is real world, as close to real world as you can get. But again, that fundamentally means any new car companies that join a new team, if they do not have that kind of money, their vehicles will be fundamentally at least 1 or 2 generations behind of you. So F1 was like, that's not good for competition. So they kind of blocked it. That should give you a context how idiotically expensive these things are. Another aspect is that India became the third nation to have hypersonic wind tunnel. This is what I'm showing you. Like, again, there is no actual photo of the main things, and be mindful, it's made for military application and is boring. That's why there is not that much press about it, but it is a very important thing. A small tunnel, again, blowback system, kind of system. And first was USA, second was Russia, third is India, fourth is China. So that should give you a context, like how expensive we are talking about. So whenever you see NASA able to test something in hypersonic, be mindful, that's a very big deal. And that means they have very solid confidence in the model. Otherwise, they're not going to waste hypersonic wind tunnel time. That's a very expensive. And again, if you are like jumbo jet company kind of thing, then you're going to have a transonic sort of system, wind tunnel for your own. That you can afford, but be mindful, small one. Not where you can put like, very large models, small ones. But these things are generally designed for continuous because that also gives them fatigue characteristics. So that's the cost. That's why generally governments build this and they rent it out to different branches. And be mindful, people generally put buildings also in them. Like, why? Hurricanes, tornado, typhoons, tsunami, those sort of things. So it's a very wise investment from a country's point of view. A private company, if they can afford it, YOLO. But if they can't afford it, generally it's a very good idea from a country's point of view to help other industry to grow. So that's why governments are spending so much money, even in China. So this was my presentation on wind tunnels. If you have liked it, please type part 2. I'll make part 2 of it. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.